So next we are going to consider the surface area of a surface of revolution from taking your parametric curve x of t, y of t from t is alpha to beta and rotating around the x-axis. So then the surface area of that parametric curve is going to be, this is 2 pi r L is what that is. So remember, surface area of a surface of revolution, you are integrating 2 pi r L. And your L actually is ds, a little piece of arc length, and then y is the radius right here. Okay, so the radius from the x-axis is actually the y-coordinate of any point along there. So we're going to find the surface area from rotating cosine cubed, sine cubed. So we're going to use this formula, but for ds we're going to use dx/dt squared plus dy dt squared square root. So you always want to find this thing and simplify it. Well, we've actually already done that in a previous example. Okay, that turned out to be, let's see, the dx dt squared plus dy dt squared. That was 3 sine t cosine t, right? Right here. 3 sine t cosine t. So I already did that once, so we don't have to redo that. So we are going to find our surface area of revolution here. S is going to be the integral. And we actually don't have to rotate this entire curve here. If we take one piece here from t equals 0 to t equals pi over 2, and we rotate that around the x-axis, get something like that. So it's kind of a spinning top, and it's set on its side. So we're just going to take this piece from 0 to pi over 2, revolve that around, find that surface area, and then double it because we've got symmetry. So we're going to do 2 times the integral from 0 to pi over 2. Remember, you always want to use symmetry if you can. And then 2 pi y, and our y-coordinate sine cubed t. And then times this guy here, which we already figured out was 3 sine t cosine t. dt. So we can take our 2 pi out in front here. So we got a 4 pi out in front. Integral from 0 to pi over 2. And sine, well, actually you can pull that 3 out also. So 3 times 4, 12, 12 pi. And then we've got sine cubed and sine, so that'll be 4 factors of sine, so sine 4th t and cosine t. And this is a trig integral. I see a function and its derivative, so let's let u equal sine t again. And du is going to be cosine t dt. So this is going to be 12 pi out in front. Integral. This will be u to the 4th and then du. And 0, plug in here. Sine of 0 is 0. Pi over 2, plug in. Sine pi over 2 is 1. So we got 12 pi out in front. And then antiderivative is going to be u to the 5th over 5. And we're evaluating that guy from 0 to 1. So plug in a 1, we get 1/5. Plug in a 0, we get 0. 1/5 minus 0 is 1/5. This is just 12 pi over 5. Okay, and that's with the doubling. 0 to pi over 2, and then double it. Now notice again here that if you would have done integral from 0 to 0, or I'm sorry, not 0 to 0, 0 to pi of sine to the 4th cosine t, then when you plugged in your substitution, sine of 0 and sine of pi, they're both 0. So you would have got integral from 0 to 0 of u to the 4th du, which equals 0. So you get canceling. And again, that's because of the orientation of the curve. So this is oriented counterclockwise. In this direction, y is increasing, but then on this piece, y is decreasing. And we're multiplying by that term y. And so this surface area gets counted positive, and then this one negative, and they cancel out. So again, use symmetry. So now you should be able to go in and try WebAssign section 10.2, problem 5.